now we're going to talk about using a double integral to find the area of a surface. Specifically, we're going to look at surface area. So a surface area is basically the solid region that's going to be wrapped around a surface, closed and bounded by a region in the xy plane. So we tend to teach this as you've got a cylinder, you cut the cylinder, lay the rectangle flat, and then have the two circles, and that is going to be how we find surface area. In calculus, we've learned that integration can actually find the surface area for us. So now we're extending that knowledge into the multivariable plane. So again, that z-axis keeps coming up again. So z is a function of f of x comma y, so it's dependent upon x and y, and it's defined across some given region R, which is going to be closed and bounded, and it's going to make sure that we have a continuous first partial derivatives. So visually, this visual here on 14.44 is really nice to be able to get a feel for what this actually looks like in practice. So to find the surface area, we would construct an inner partition of the region, which would be consistent of n rectangles. So we're going back to that Riemann sum definition here, where the area of the ith rectangle is going to be given by what we have with the change in area is related to the initial change in x and initial change in y. That's definitely not how we actually want to execute this, but we want to understand that we're chopping up that surface area into small regions like we would if we were doing a Riemann sum. Now, to be able to make this happen, I can start to divide these up into vectors. So I can have my u and v vectors like we've already seen in the derivative section. And these u and v vectors can be then used to describe the area. So I'm going to have those lovely determinants come back so that the area is going to be given by the magnitude of the cross product. So to find the cross product, I'm going to have to set up my matrix based on my I, j, and k that we have here. And then I'm going to have to find the determinant of that. Then once I have that, I would find the magnitude by doing the square root of the components being squared. Now, if I look at those components, should look familiar. And so the surface area would then be the sum. So I would be taking those magnitude of the cross product, and I would just be multiplying it by basically the change in area. So if I want to really simplify my life and get a formula, this would be the formula for this whole proof right here. So I would have a double integral to be able to express it, and I would be utilizing that magnitude equation where I've got the components being squared. So an aid to help you remember this is that if I'm looking for arc length, this would be the formula I would use here. Area and the plane would be the double integral I would use here. So this is from Calc 1. And then surface area is the new piece that we're extending into 3 dimensions here right now. So what does this look like in a question? That's a lot of theory. So to find the surface area of the portion of the plane that's described by 2 minus x minus y, and lies above the circle in the first quadrant, I would draw it as seen in this image. So that's going to help me visualize what does this thing actually look like. It's not anything that can easily be found with a geometric formula, but I can visualize it. So then I'm going to take the formula for it and have 1 plus that fxxy squared, fxxy squared dA. So where do those 1s and negative 1s come from? Well, if you look at this, I have 1 on the x-axis and I have 1 on the y-axis. So I have some 1s here. I also know that it's going to lie above the circle that's being described here by x squared plus y squared is less than or equal to 1. So I know that that's happening. And then I also have those components. So let's think about, I have 1 and 1 here, but what happens if I take the derivative of this with respect to x? If I take the derivative of this with respect to x, that's going to give me a negative 1. If I take the derivative with respect to y, that's also going to give me a negative 1. And look at how nicely that pops in here. So when we're doing this, I'm looking for that derivative of x with respect to x, derivative of y with respect to y, and I'm going to square them, which gives me the square root of 3. So I can pull that square root of 3 out front because it's a constant and just integrate dA. So I know that I have square root of 3 times the area of that region. R is a quarter of a circle with radius 1, from what I just showed you in the image, with an area, if it's a quarter of a circle with the radius of 1, then this would how I get to be to pi over 4. So I'd have square root of 3 times the area of my R, which is pi over 4, and that's where I get square root of 3 over 4 times pi. So notice I'm not necessarily completing the integral here. These are not definite integrals. I'm having to find what is dA is the derivative of area. The integral of the derivative area is the actual area. So what I did was I found the area because this region at the bottom is a quarter of a circle. So that's where this is coming from. You're going to have to pick it apart a bit visually. So please make sure you are using those visual pieces.